Alright, so take a minute, read the problem, draw a picture, definitely, even if you're not willing to put the time in to try to solve the problem, because we already did it in class, then definitely draw a picture, because that helps. I have a real eraser today. Luxuries. Okay. So, picture drawing time. Drawing the system from above. Our table. Have our rod. Make the table bigger so it looks like it could actually spin on it. Okay. So this is our rod. It's length L at L/2. The bullet gets stuck in it. It's the path of the bullet. Right, so that comes shooting in, literally, and embeds itself in the rod at L/2. Okay, so it's a frictionless table, frictionless axle, so once it starts spinning, it'll spin forever in this magical world of no friction that the problem has given us. Okay, so first, what do we know about collisions? We know momentum is conserved, always. So in this case, we will use angular momentum, since it's spinning things. Angular momentum of the bullet. This is right as it enters the rod, not after the rod starts spinning, but right as it enters. M/4, because that's what the problem gave us, times its radius of spinning, which is L/2, times its linear velocity, which is given to us. Okay, so that'll be useful later. What else do we know? Well, since momentum is conserved, we want to be able to use this V and this M along with the moment of inertia of the system to solve for the unknown of omega at the end. That's what we want. And bullet. Okay. So if we do that, we should only have one unknown, and that'll be omega, and we'll solve for that, and we'll be done. Okay, so you may have memorized this by now, but if not, you can always look it up. Hopefully it's on your equation sheet. The inertia, the moment of inertia of a thin rod, right, 1/3 ml², plus the point mass of the bullet, which is just the mass. There's no mass distribution, so it doesn't need a fraction out front like this does. Over 4. In real life, of course, there would be a mass distribution, but, you know, it's kind of like the frictionless table. It's a lot easier this way. Okay. And this is its radius, right, of how it's spinning. And the rod is spinning like this around it. pretend that's a good picture. Okay, and then just add them up. And this is moment of inertia of the system after the bullet is embedded in it. And it's been spinning. So you can add it up if you like. Comes out to 19 over 48 ml squared. Okay. That's our I total for the whole system once the bullet is embedded in the rod. Okay, so we have moment of inertia. We have the angular momentum of the other side. So now we can actually do stuff. Let's see. Better if I can write without destroying this. I'll erase my picture. Okay. So, care about this. Care about I total, right? Because that will help us find omega, like so. Since angular momentum is conserved, you can say m over 4 times L over 2 times V is equal to 1948 you know what this is equal to. ML squared, and that is times omega. Okay, then we just solve for omega, which is pure algebra, nice and easy, and you get 48 over 19 Z over 8L. That's just moving this over here, dividing this by this, equal to omega. And that gives us final 6V over 19L. Alright. That wasn't that bad. So we just found angular momentum of before and after, and the only thing that was missing was the angular velocity, so we just solved for that. Okay, I'll leave that up there because we get to use that for the next part. Okay, and part B asks for kinetic energy. So, kinetic energy of the bullet. This should be pretty simple for you. Calculated many kinetic energies by now. M over 4, because that's the mass of the bullet. This is the initial energy of the system when the rod is not spinning. Times V squared. Okay, Kf it's a little more interesting because now it's angular, right? It's 1/2 I total. I'll write it down steps, less confusing. I total omega squared. That's the general formula. That's equal to 1/2 19 over 48, right? Yes. 19 over 48 is kind of a silly number, hard for me to remember. And then times omega squared, which we found, 6v over 19L squared. Okay. So we just divide one by the other. I will simplify this. 1/8 mv squared. Okay, that looks a little nicer. So we just divide one by the other, right? Yes. And you get Ki over Kf, because it's asking for the ratio of the initial to the final. So when they do that, you just divide the initial state by the final state. And you get (3 over 19). I'll let you do the nasty algebra, you know, if you really want to. But you get the idea. You know, it's going to be 1/2 1948 ml squared times 6v times 19L squared. And you just divide it by a much easier number, mv squared. You know, you can work that out yourself. And it all cancels nicely, and you get 3 over 19. If it doesn't cancel nicely, that means one of your things was not kinetic energy, because if you get a unit out of a ratio of two of the same kind of unit, that's a problem. That means you messed something up, and your fraction is incorrect. If you have a ratio of initial to final energy, velocity, acceleration, torque, whatever, it needs to be unitless. So yeah. So have fun. Good luck on the test. And I hope that wasn't too bad. I didn't think it was.